Polynomial functions, other than power functions, have a few special characteristics. Even power functions can have these. Why can? Let's think of, y equals x. Will it have a local maximum? Well, actually, over any given interval of a function, indeed, you will have a local maximum even on y equals x, which is a straight line, because, hey, let's take this interval. What is the highest value that can be reached on this interval? The highest value. Seems pretty, well, admittedly, that's a little bit nitpicking, but the point is that a local maximum is the greatest value on a certain interval of a function. The local minimum is the smallest value, or most negative. So, what happens when we have a number of these? Well, we can have maxima, local maxima, or minima. And of course, we have such things as absolute max, maximum, or maxima, and of course, absolute minimum, which is over the entire domain of a function. Now, for odd degree polynomial functions, let's compare the graphs of each group of functions. So first, we have x to the third power and negative x to the third power. Are there any absolute maxima or absolute minima here? Or even local maxima and local minima, others in the sense of, okay, let's say we take this part. Of course, this is going to be the maximum and that's going to be the minimum. Besides that, we mean in the sense of, the values on either side, immediately to either side, are bigger, or the values to immediately to either side are smaller. So besides that, well, no, we don't have such a thing. But what about here? Here, we see that if we invert all the signs, not only does this get vertically inverted, it also gets horizontally inverted. And we notice that we now have local maximum and local minimum. These are, of course, not absolute maximum or absolute minimum because, hey, this goes to positive infinity and negative infinity. Now, how do these smaller degree terms interact with the highest degree term to produce this particular shape instead of just being an x to the third? Well, it's because we have this coefficient here that magnifies the impact of the even power, while the actual numbers involved, that's being taken to the exponent of, is relatively small in magnitude, so in total size. And here we have a plus 5x that wrestles it back slightly toward the, this end goes to negative infinity, that end goes toward positive infinity, compared to what this would have done otherwise, which would have resulted in a much bigger tip over there. And we have the plus 2, which of course moves the value at x equals 0 to 2. Just by looking at the equations, you can actually see a number of changes that can be brought about by the coefficients of lower degree terms, such as this one. Here we see, negative x to the fifth. That's this line here, this blue line. Now that has no local maxima or local minima, whereas this one here does. Negative x to the fifth indicates that we're still going to end up starting at when x approaches negative infinity, y approaches positive infinity, and, well, the other way around. So, what about the 2x to the third power? Well, that would have been like this. So, for this part, because of the 2 coefficient, It happens to be that x to the third power times 2 is bigger in terms of impact than negative x to the fifth power. And the plus x also helps by adding positive value here and taking away value, so adding negative value over here. Thus, we can warp the graph, but we notice that this graph here, it is still symmetrical about the origin. Why? Because every single thing that we're adding together or subtracting is symmetrical about the origin. They are all odd-powered functions, or odd-degree polynomial functions. So, the general rule is that if the leading coefficient is less than 0, then you will end up approaching positive infinity in terms of y value as x approaches negative infinity. So you will be going from quadrant 2 to quadrant 4. And if the leading coefficient is positive, then you will go from quadrant 3 to quadrant 1. We note that the y-intercept is, of course, a constant term, because if you set x equal to 0, everything but the constant term disappears. The number of x-intercepts is limited, and it is less than or equal to n and greater than or equal to 1. Why? Well, I mean, if we're going to end up going in opposite directions relative to the y-axis, as in going to plus infinity and minus infinity, we're going to have to cross the x-axis at some point, right? So it has to cross at least once. The most number of times it can cross is equal to the degree of the function. Because no matter how you mess with it, well, you are only going to be able to mess with it in so many ways, and thus you will end up with this holding true. So many ways being, oh, how many lower degrees can I add to this or subtract from this? Because the highest degree term is to degree n. So the domain is x such that, that's how this is read. This set notation here, this is read as x such that x is an element of the real numbers. And the range is y such that y is an element of the real numbers. This holds for all odd degree polynomial functions, even if they have even degree terms. But if they only have odd degree terms, in other words, not even a constant, and no even degree terms either, then they will be symmetric about the origin, because every single one of those terms themselves is symmetric about the origin. So if you stack them all together, it's still going to be symmetric about the origin. So even degrees. Well, compare the graph of each group here. Use your graphing calculator. We point out that graphing calculators are great as an educational tool, but if you end up reliant on it, that generally does not bode well for certain exams which don't allow it, and of course for contests, which often don't allow calculators of any type. So here we have y equals x squared and y equals negative x squared. Obviously, these end up going in very opposite directions because the leading coefficient is of different signs. Now, here we see that the range is not, oh, y is an element of the real numbers, because we have a maximum or a minimum, depending on the sign of the leading coefficient. here we see some changes being made. Why is it that one of them happens to be offset a certain way? Y equals x squared minus x minus 2. And this down here is y equals negative x squared plus x plus 2. Well, between these two, actually, we didn't even need to look at the coefficients or whatever. We just needed to look at the sign of the leading coefficient to figure out which is which, because they open in opposite directions. Now, a parabola that opens down will always have negative leading coefficient, and one that opens up will have positive. So, how were these changes made? Well, minus x. What does that do initially to the part where you end up having x squared as smaller in magnitude than x? So, say from 0 to 1. Well, that moves that part down, and the other part under 0, well, what happens to that? Oh, minus x. That means it gets lifted up a little bit. And then, of course, there's this minus 2, which moves this entire thing down. And for here, we have the same idea of, hey, what happens when plus x bumps this part of what would have originally been a parabola pointed down like this? This part gets bumped up, that part gets knocked down. So overall, the whole thing turns a little bit, or seems to. It doesn't actually turn. It's still pointed straight down. The axis of symmetry is still vertical. But we can think of it as kind of like doing this. But anyhow, that's how this ends up having a bump over here. And the plus 2 is, of course, just sliding it up. So here we can compare the graph of these two, and we get that negative x to the fourth power. The other one is positive something, x to the fourth power. Obviously, the one that opens down is going to be the negative one. So this is f, and this is g. Now, as we can see, there can be multiple local maxima and minima. Now, the number of local maxima and minima depend on the degree of the function. We noticed earlier that if it was a function of degree 2, we always had a parabola. So we could never make a bulge or whatever in the middle of the parabola or something similar. So we can conclude that the number of maxima and minima put together must be less than or equal to extrema is a general term for maxima and minima. This is less than or equal to n minus 1. N is the degree. Of the polynomial. So, for odd functions, or odd-powered functions, if you prefer the long term, the number of extrema can be as low as 0. But for even functions, or even-powered functions, you will always have at least one extremum. Because, it eventually bottoms out and goes back in the same direction it came from with respect to y. So from y equals positive infinity to y equals positive infinity. Or the opposite. So negative infinity to negative infinity. But regardless, here we could identify which was which based immediately upon the sign of the leading coefficient. But even if we couldn't do that, we could always look at the intercept. So one of them is plus 1, the other one is minus 1. So which one's plus 1, which was minus 1 is immediately obvious upon inspection. But if neither of these two criteria can distinguish two functions, then you need to look at some of the numbers and say, oh, x equals 1. Let's see, one of them has a value that's this, the other one says that. It's easiest if you have one that's above 0 and one that's below 0, because then you just need to work out which one's positive, which one's negative for that particular x value, and that's it. So here, we draw some conclusions. If an, so the leading coefficient, is less than 0, the graph will begin in quadrant 3 and end in quadrant 4. 3, 4. It will begin in quadrant 3 and end in quadrant 4, or if you want to talk about it in the reverse fashion, then begin in quadrant 4, end in 3. It will poke up potentially into 1 and 2, because it's of course possible that it just doesn't, like this parabola here. Now what about here? If the leading coefficient is positive, then at x is positive infinity or x is negative infinity, y goes to positive infinity, which means that we will have our beginnings and ends in quadrant 1 and 2, or 2 and 1 if you prefer. So the y-intercept is still the constant term, because if we set x equal to 0, everything else disappears. Now the number of x-intercepts can be anywhere from 0, because hey, we're starting at positive or negative infinity, and then we're going back the same way. Do we have to cross the x-axis? No. But if we happen to do so, then we can go up to n crossings. So say we have to the 4th power, we can have something like this, where we happen to subtract a lot in terms of coefficient times some x to the 2nd power. That's a way you get a w. Now if you have only even powers, including the constant term, then you can have it symmetrical about the x-axis. But as soon as you add an odd power in there somewhere, it breaks the symmetry. So the domain is written the same way, x such that x is an element of the real numbers, and the range is going to be y smaller than or equal to maximum, or y larger than or equal to minimum. Depending on how picky your teacher is, you might actually have to write, oh, left bracket, so set of y such that y is smaller than or equal to maximum or bigger than or equal to minimum. Some teachers even ask that you write y is an element of the real numbers and then write. So say it like this. Now, in terms of the number of local maxima and local minima, it has to be less than or equal to n minus 1. As mentioned previously, this is a general characteristic of all polynomial functions, and another one is that the nth difference is called the finite difference principle. The nth difference is going to be equal and have the same sign as the leading coefficient. Now, if you do calculus, this will be particularly familiar in terms of first differences, second differences, and so on. The nth difference is going to be equal to an, so the leading coefficient, multiplied by n factorial. What is n factorial? N times n minus 1, n minus 2, dot, 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 times 2 times 1. So multiply all these numbers between n and 1 together, inclusive of both ends. So here we see a table of differences, or more specifically, a table of finite differences, because we don't do, fifth difference, which would be 0 for all of them. So what is the order of the polynomial? Well, we know that for a polynomial of some degree n, when we get to the nth difference, it will be constant. So for, say, a straight line, what is the difference between x equals 1 and x equals 2 and x equals 3 on, say, y equals x? Well, we know that it's 1 and 1. That's the first difference, and it's already equal. What is 1 factorial? That is 1. So the order of the polynomial is fourth order. What is the leading coefficient? Well, we know that 24 a subscript 4 times 4 factorial. So a subscript 4 is equal to 24 over 4 times 3 times 2 times 1. So this is equal to a to the 4 equals 1. Okay. So we have the leading coefficient. What is the function? So here we have y, right? So not fx. Well, right, y equals x to the 4th plus a3 x to the 3rd plus a2 x to the 2nd plus a1 x to the 1st plus a0. What do we actually find when we look at this? Well, first of all, we found a0 equals 0. Because at x equals 0, y equals 0. And then what? At x equals 1 or negative 1, y is 1. So x equals plus minus 1, y equals 1. This leads us to one conclusion. First of all, this term doesn't exist. Why? Because x to the 4th covers this. a2 equals 0. And then we look again. Negative 2 and 2 for x give us y equals 16. So, what does that tell us? That tells us symmetric. Note that this only works when you stack it together with the first bit of information. X plus minus 1 is symmetric. Trick about x equals 0. So what we get is a3 and a1 equals 0. So the function is y equals x to the 4th. Now, hopefully, this was a good review of things we hopefully a new part of, at least, from polynomial functions in general, learned last year or whenever. So that's it for this section, and we'll see each other again then, next section.